Hello, sophomores. We are officially done with energy, although we might find ways to connect what we're going to do next to it. But we're not done, or we're done just studying energy on its own. And we're going to start studying something called interactions. This is an introduction to the concept of momentum, which is about interactions between objects within a system. So up until now, we've talked about single objects and their motion, or forces acting on single objects, or forces acting on a system of objects. And now we'll deal with multiple objects in a system interacting with each other. Here is our first generic interaction. This is the before state of the interaction. We have a mass called m1 going a velocity v1 toward a mass called m2 with a velocity of v2, and they're going to crash into each other. During the interaction, because they've crashed into each other, they exert forces on each other. This is force on 2 by 1, that is, block number 1 is pushing block number 2 to the right, and here is force on 1 by 2, which is to say that block 1, or the force on block 1 by block 2, pushes from block 2 to the left on block 1, pushing it to the left. The after of this generic interaction, in this case they've bounced off of each other, and we have m1 moving to the right with a velocity that's a new velocity called v1 prime. This little apostrophe here is read prime. And m2 moving to the right now with a velocity v2 prime. What we're about to do is to look in detail at the during phase of the interaction, and we're going to prove something that we would have tried to gather evidence for in person through experiment if we had been in school. But since we're not in school, we won't do our air track experiment, and instead we'll be thankful that we can prove what is true about momentum and interactions from basic principles. First of all, during the interaction, we know from Newton's third law that the force on 1 by 2 is equal and opposite the force on 2 by 1. Equal and opposite meaning they're the same size and in opposite directions from each other, so we get a negative sign added in. This means that mass 1 times acceleration 1, that is the mass here times its own acceleration, is equal to the net force on it, and that is equal and opposite mass 2 times acceleration 2 during the interaction. This is a slightly different proof than the one in your notebook, but the same thoughts apply, and it's equally valid. Mass 1 times acceleration 1 can be rewritten as, by the definition of acceleration, delta v1 over delta t, and force on 2 by 1 can be rewritten negative mass 2 times delta v2 over delta t. The change in velocity for either of these objects depends on their starting speed and their ending speed, and so we can write the change in velocity 1 as v1 prime, the final velocity, minus v1, and we can write the change in velocity of object 2 the same way, as v2 prime minus v2 over delta t. The delta t here is the amount of time that the collision took to take place, and since it's present on both sides of this equality, it can cancel, and so we're left with m1 v1 prime minus m1 v1 equals negative m2v2 prime minus, plus, if we distribute, plus m2v2. If we rearrange this expression now from before to after, we'll remember that the before quantities did not have primes on them and that the afters did. So we'll put the befores and the afters with each other. What that means is that this term and this term will end up on the same side of the equal sign. So we'll do that like this. m1v1 plus m2v2 goes together on the right side of the equal sign here. And m1v1 prime plus m2v2 prime is together on the other side of the equal sign. Here again is the result of that proof. It is that m1v1 plus m2v2 equals the new m1v1 plus the new m2v2. This is before and after the interaction has taken place. Momentum, which is our new topic, is defined as m times v. Its units are kilograms times meters per second. There are no shortcut units like joules or newtons for momentum. And the big idea and the result of the proof can be written in many different ways. Here it is a different way. If we define momentum to be p, which is mv, then this mv and this mv added up equal the mv added up both before and after the interaction. Another way to write this is that the sum of the momenta before the interaction equals the sum of the momenta after. This is a Greek letter sigma. It's a capital sigma, and it often means add a list of objects or items up in mathematical contexts. Here it is written out kind of longhand. Here's another way to think of it, that if we add up all of the MVs before and after the interaction, they have to be equal to each other. That should remind you of what we just finished doing with energy, which is that we dealt with the conservation of energy. So here is a fact that was proven. It is that momentum is conserved in all interactions. Conserved meaning it's the same before as it is after. Momentum is conserved over time, whereas energy was conserved over location. We said that the total energy for an object was the same in any place as it is in any other place. What we're saying here is that in a system, if there is an interaction between the parts or objects within a system, that the momentum in total of all of the objects that make up the system will always be the same before, during, and after interactions of the pieces. Now that you've seen a proof of the conservation of momentum, we're going to run through several examples of both actual physical situations where momentum is conserved and also how to solve problems involving conservation of momentum in different situations. So the first series of demonstrations here are all called bounces. In this case, we have a mass of 1 and a mass of 1, and when a mass of 1 hits another mass of 1, in the before state, the first one is moving, and the second one is stationary. And just watch what happens. That one took off, this one stopped. Here's a second scenario that's again a bounce, and here a mass of 2 is going to collide with a mass of 1. Watch what happens. The lighter one took off going really quick, and the heavier one kept moving but slowed down after the collision. last bounce is, what if a light object hits a heavier one? Here goes. Okay, we do have a bit of friction here, but maybe we can show what I'd like you to be able to see if we have an extra heavy object being hit by a light one. So this is a mass of 1, this is a mass of 3 that it's going to run into. There, you see that the lighter object not only stops, but actually ends up going the opposite direction, while the heavy object that gets hit takes off with some speed. Suppose now that we explore a situation where two masses did have the kind of interaction that you just saw, that is, that they bounce off of each other. I'll now show you how to use the conservation of momentum to solve problems that are like these sorts of situations. For our example, we'll imagine that in the before state in the system, there's a mass of 3 with a velocity of 4 headed toward a stationary mass of 1. In the after state, let's imagine that we measured the speed of the 3 mass to be 2. The question would be, what is the speed of the 1 mass? In other words, v1 prime is our unknown. In order to use the conservation of momentum, we should add up the momenta of all of the objects in the before state. So what we'll write is mass 1, which is 3, times v1, which is 4, plus mass 2, which is 1, times v before for that mass, which is 0, has to be equal to, by conservation of momentum, 3 times 2, that is this mv after, plus 1 times the unknown, which is the final velocity of mass called 1. Solving, we get 12 equals 6 plus 1 v1. Subtracting, we end up with v1 prime is 6. This makes sense compared to one of the examples you just saw, which is that if a large mass hits a small one, the large one keeps going but slows down, and the small one takes off and goes very fast. The next scenario is called a coupling. These carts have on one end or the other Velcro, and that Velcro is designed to make them stick to each other in a collision. So we're going to see what happens, at least qualitatively, that is with no numbers, when an object with a mass of 2 runs into an object with a mass of 1, and instead of bouncing off of each other, they stick to each other. Here goes. We could also see an object with a mass of 3 crash into an object with a mass of 1. And you should notice that after the collision, the combination or the coupled set of cars has slowed down compared to how fast the original car was moving. Now let's analyze a coupling situation with numbers. In our example, we will, similar to what you just saw, imagine that a mass of 2 heads toward a mass of 1. Let's suppose that in this before state, the mass of 2 has a velocity of 6. In the after state, for this to be a coupling, which means that these two masses will stick together in the end, they will end up moving together with the same velocity as each other as a combined mass of 2 and 1. And our question here would be, what is their final speed? Again, using conservation of momentum, we would say mass 1 times velocity 1 before plus mass 2 times velocity 2 before equals the combined masses, which is 3 times the velocity we're looking for. In this case, we end up with 12 equals 3v, or that the velocity will be 4 for the combined or coupled masses in the after state. This again lines up with our reality, as you just saw a heavy car hit a lighter one, and when they coupled, the coupled pair of them slowed down compared to how fast the original one was moving. The third type of interaction we can look at can become a little bit quantitative. Here we have two equal mass cars that are going to explode. When we say explode, we mean it physically, where when I push this button, there's a spring that's been compressed, it's going to decompress, and it's going to push on the car on the right in your view. That car on the right is going to push back on the car on the left, and they're going to push with equal and opposite forces on equal masses, so they will experience the same acceleration for the same period of time and pick up the same velocity. We can prove that by noting that they will travel the same distance in the same amount of time after the explosion. So I've set up targets, walls, for them to crash into that are the same distance away from each car. Here goes. Of the object on the right that has a mass of 1. Because this has twice the mass, but will have an equal force applied to it as the other car will, it will experience half the acceleration and half the change in velocity, meaning this one, the one on the left, will end up going half as fast as the one on the right. Because of that, it will only travel half as far as the other one in the same amount of time. So I've set up walls now such that this distance is half as long as that distance. Here goes. Finally, let's look at an example of an explosion. In this case, in the before state, we will have a 2-mass block sitting coupled with a 1-mass block. This type of interaction is also sometimes called a decoupling, because in the before state, the two objects are coupled. They are together. Let's suppose that in the after state, the mass of 2 moves to the left at an unknown speed, and the mass of 1 moves to the right at a speed of 8. Again, we can apply the conservation of momentum. In the before state, the mass is 3 and the velocity is 0. And in the after state, we have 2 times v plus 1 times 8. we end up with, in this explosion example, 0 equals 2v plus 8. If we subtract, we end up with 2v equals negative 8 and v equals negative 4. There are a couple things to see here. One is that the velocity comes out negative, and it should, given that we defined the right direction, the to the right motion, to be positive velocity. The 2 mass has to end up going to the left or in the negative direction in order for the total momentum to still be 0 in the after state. Also, we notice that the 2 mass, being twice as massive as the 1, ends up going half the speed in the after state.